Okay, I'm back, and before the break I was fumbling around with this formula for P of x, trying to tell you something, and I want to just backtrack a little bit and explain it. I'm going to take these this E10 times F10 off, so get back just to the first part of this formula, the n factorial divided by x factorial times n minus x factorial. Let's look at that again. Draw that down. What this is doing, you can refer to this on page 221. It's the number of ways to arrange x successes among n trials. Now, think of it this way. Cast the hook the first time. What are you going to catch? A fish or not a fish? Or no fish, right? So there's two possibilities there. Second toss, you can have a fish or no fish. So now we have four possible outcomes. If you take this tree, as we've done in other examples, and draw it out to the level of 5, there's a certain number of outcomes that occur. 2, 4, 8, 16, 32 possible outcomes. Now, how many ways are there of getting 2? Well, of those 32 possible outcomes, 10 of them would have 2 successes, and 10 of them would have 3 successes. And you can figure that out: 10, 20, 26, 30. In fact, this all adds up to 32. So this is just the number of nodes on a tree at the end of the day. So there's one outcome, 5 tosses, no fish, and there's one outcome for x equals 5, 5 tosses and 5 fish. And there's 5 outcomes where you'd have 2 or 4, and 10 outcomes with 2 and 10 outcomes with 3. Okay, so that's just by way of giving you a little explanation of what this first thing is. So all we're doing is taking the number of outcomes in each case of each value of x, multiplying it by the 2 probabilities to get the probability of that outcome. Just that's what's going on here. Okay, now what we want to do is answer some questions using this. But before we do that, I'm going to show you another way to handle this, an easier way. And I'm going to give you the Honest John's handy-dandy binomial calculator function. Oops, I got the answers in here. I've been practicing. Get those out. These are the problems that the book has asked us to work on. And here is the formula, the table, and I will post this in the content area of Desire to Learn, so you can use it too if you wish. All you have to do is open up the spreadsheet, copy this area here onto your spreadsheet, and it will then be available to you to do calculations. Now, there's 2 parameters, the number n, in our case 5, and the p value, 0.3. This formula is smart enough to figure out q all by itself. You don't have to tell it that. So what we'll do here is use the binomial distribution function. And the parameters of that, if I click inside the formula somewhere, are first of all the number of trials. A38 in this case is x. This is the x value. I don't know why they call it number under bar s. They do. The number of trials, C36 is here. That's 5. And the probability of a success is here, E36, and in our case it's 0.3. Now you notice I put all the dollar signs in here, so I drag this down. The final parameter is 0, which means cumulative, and so we don't want it to be cumulative. We want the individual values for each value of x. Now if I take this same formula and paste it in over here, did it a different way when I set this up, but I'm going to now just use this exact same formula, except I'm going to change the last value to 1. Now I'm going to get the cumulative. Now for x equals 0, there's no accumulation to do, so it's always the same. I drag this all the way down. Now what I've done is to give me the cumulative distribution of 0.16 plus 0.36 is 0.52, give or take a little extra. And so you can see that by the time I get down to the last value of x, we're up to even unity, which means is exactly what we would hope for, is that all the probabilities add to 1. So here's the table, and rather than going through all this nonsense, I can simply use this table. Now, one of the values, one of the reasons for plugging in parameters into these formulas rather than writing in hard numbers is that if I want to go in and change something, let's say I want to say, there's no chance, no way, the probability is 0.3. Let's make it 0.1. Well, two things happen. The probability of catching no fish goes way up, and the probability of catching 5 fish goes way down. But I can do these little, what if the probability is 0.5? Catch a fish every other time. Well, now it's a nice even symmetrical distribution where probability of 2 and 3 is exactly the same. The number of outcomes, remember that this part of the formula still would be 10 and 10, but because a success and failure has the same probability, the two probabilities end up being the same. So, nice thing about parameters, what I'm trying to say, is you can go in and play these games. Okay, now the final part is easy. Now that we've done this, we'll use this table to answer the questions. It's the same as the one up above. What is the probability that x equals 3? Well, you can pick that right off the table. Go down the column to 3, go across to the individual, not the cumulative, but the individual value is 0.1323. I hope that's the right answer. Look it up in the back of the book. If it's not, I'll be terribly embarrassed. Now, what's the probability that x is equal or less than 3? Well, I could add up this. That's 3, less than, so I want 2, 1, or 0. 0.96922, but look right here, I have it already. I didn't have to do that. I could just use the cumulative side of this and pick it right off the table. What's the probability that x is less than 3? Well, we already did that. No, we said less than or equal to 3. This time we want just less than 3. So it would be 2, 1, or 0. They're all less than 3, so I can just use that number, 0.83692. What's the probability that is greater than 4? Oh, a trick question. So I could say that's equal to 4 or 5.03, but I could also say it's equal to the inverse of that it is less than or equal to 3. Right? So if I take equals 1 minus less than or equal to 3, I get 0.03. Same deal. X, what's the probability that x is greater than 2? Well, this time I'm going to use the sum function because there's too many to add up here. Greater than 2. So I don't want 2 itself. I want 2, 3, 4, 5. And there we have it, 0.16. So you can see that once you have the table, the hard part in these problems is to get the table going. Once you have that, then you can go on and answer all sorts of questions about this. Were there other parts of this? Oh yeah, it wants us to calculate the mean, the variance, and the standard deviation of this distribution. Show that the formula. Calculate the intervals. Okay. Well, you can do these pretty easily, but let's just make sure. I'll calculate the mean and the standard deviation for you here. I'll give you the page reference for this. Oh, it's right here above us on page 228. The mean of this distribution is equal to n times p. So I'll put mean is equal to n times p, or 1.5. The average number of fish that you're going to catch when my granddaughter goes fishing, 1.5. And what is the variance? Well, it's equal to n times p times q, which is really 1 minus p. There's the variance, and the standard deviation, of course, is equal to the square root of that. And so 95% of the time, I'm going to be able to say that my granddaughter is going to catch somewhere between that minus 2 times that. Whoops, wrong one. They're about the same. Not much difference. Oh, I put it in the wrong. I just typed it. Equals that minus 2 times that. 2 standard deviations below. Okay, all right. So less than half a fish, I don't know how you get that many, equals that, where's the plus here, plus 2 times the number of standard deviations. So 95% of the time, my granddaughter is going to catch between 0, because there's no such thing as negative half a fish, between 0 and 3.5 fish. It's like how many kids does the average person have. Okay, that's enough for this week. We'll see you online.